Okay, we're back with the second part of the session three. So now I'm going to talk about the relative phase that is very important for us to also understand. Like if you are on the equator, your theta is fixed as pi over 2, but your azimuthal angle phi can vary freely. Basically, it can sweeping around the equator. So let me draw this. If you have an light sphere like that. So let me change the color here. So if you're on the equator here, you can move around in the circle. So here your theta again is fixed, and that's going to be pi over 2 because that's an angle that you are building with z here. This angle is theta. And you're just moving around in the surface of your light sphere. So this is clear, I guess now. So that takes you from the state one to state plus. And we have talked about that. Now there are some, let's make a mathematical representation of the states that we have. I'm going to draw that circle one more time. Not the circle itself, the light sphere. Let's say this is my light sphere. Again, I have this is the z, right? That we have a state 1 and a state 0. And also we have a state here that is x that was plus and minus. And also we have one more state that is I. Or might be the same as I that you know here, I and minus I. Okay, so if you're in the state plus here, you can also write it exactly with this representation. So again, this is equals to state 0 plus state 1 divided by square root of 2. And state minus, that is right here, is going to be 0 minus 1 divided by square root of 2. These are states that are completely uncertain, measuring because like if you are in this state plus or in minus and you measure the qubit, the result might be 0 or 1. We don't know that for sure. I mean, there is an actual equal chance that you will get 0 or 1. Because after you measure the quantum states, the result either going to be 0 or 1. So have that in mind. Okay, let me just remove here. Now we have global phase and relative phase. When I talked about the global phase, basically I mean that the entire state is multiplied by a phase. For example, here gamma. So it does not really change the position of your state or change the position on the light sphere, and it is not physically observable. And relative phase is something that is very important. And that's a phase that is between state 0 and state 1. And it is observable, and it is a hidden variable that makes the quantum computer very powerful. So again, that's the difference between 0 and 1. Let me draw that, maybe write this so make it easier to understand. Let's say this is your state is equals to alpha 0 plus e to the power of I phi 1. So you see, this is the difference between the phase difference between 0 and 1. Just have this in mind. Okay. Now, there was an interesting discussion around it back in 1905 and 1900. That was about the wave particle duality. uh, because a lot of people just believe that particles are behaving like wave. But later on, especially the work of Einstein did a lot of contribution towards that the wave can be both a wave and a particle at the same time. So how cool is that? So before we measure a particle, the qubit can behave like a wave. But when you measure a qubit, then it behaves like a particle, which means that it can be either in a state 0 or 1. So yeah, have that in mind. And changing the measurement basis. Also, you can change the basis for your measurement. Let's say mainly we do the measurement in the basis 0 or z-axis, but also you can apply rotation gate. So for example, you can bring from a state 0 or from a 0 axis to to x basis. Let me show you how that's possible. So again, if I have a light sphere, and let's say currently I am in a state here, 0. So if I apply an H gate or Hadamard gate, that I'll talk about it more later, Hadamard over 0, it will bring my state to plus. So I could change the state, right? I moved from 0 to plus. So it's going to change from 0 to plus. I'll show you more representation later today. So the coherence is a very important problem in quantum computers today, because we know that we have to cool down the quantum computers to, for example, 15 millikelvin. That is actually colder than the outer space. This is something very difficult and very expensive because, I mean, is much, much colder than the room temperature that we work on. And also, if you even have the quantum computers that is working in the, let's say, a millikelvin temperature, and you have to anyway connect it to the outside world because you have to transfer at the end that state to a classical computer, then that connection also can create disturbance and can create also interference, and also can like decohere the quantum states. And also the coherence time also, like for example, we do all these efforts and it gives us only, let's say, 100 microsecond. So we don't have a lot of time. So that's why we have to do the measurement very quick. But just know that it's not like always that all quantum computers have to be in 15 millikelvin. Some actually can operate in the much higher temperature too. But it depends on the material and the technology that you're using. So in classical bits, we are dealing either with 0 or 1. So there is no really freedom, right? But in qubit, we have 2 degrees of freedom. Either you have theta or phi. So the qubit can occupy the point on the surface, and you can move all around the surface, right? So that allows us to even have complex phase in the quantum computer, something that wasn't really possible with the classical computer. Now, let's do one interesting example together. We have an state. We want to solve 3 problems. One of them, we want to find the probability of 0 and 1 here. So this is alpha. Alpha is equals to 1 over 2. And the probability of 0. Now, probability of 0 would be alpha squared, and that would be 1 over 4. And this is beta. So beta is equals to the square root of 3 divided by 2. So probability of 1 is equals to beta squared. And that's going to be 3 over 4. So 75%, this is 75%. 75% chance, if you do the measurement right now, we'll get 1. And 25% chance, if we do measurement, we'll get 0. So that shows the probability. And also you want to check the normalization. If you remember, I said alpha squared plus beta squared should be 1. And that's true because 1 over 4 plus 3 over 4 is 1. And if you want to find the coordinates, we know that alpha is cosine theta over 2. So alpha is equals to cosine theta over 2. And this is equals to 1 over 2. So this means that theta should be 2 pi over 3. Because we know that the cosine of, if you put it here, pi over 3 that is 60 is equals to 1 over 2. So we know that cosine of pi over 3 is 1 over 2. So it means that theta over 2 should be pi over 3, means that theta should be 2 pi over 3. Now we could do the same for phi. We know that I is equals to e to the power of ip divided by 2. So it means that it's actually not the conclusion, is equals to I phi divided by 2. I think I made a mistake here. I phi, it should be not I phi divided by 2. So it means phi is equals to pi over 2. So we can find the coordinates, we can check the normalization, also we can check the probability if you are going to get 0 or 1. Let's talk a little bit about gates, like AND and OR gates that we saw before about the classical computers. We have quite similar gates in quantum computers. Again, all of them have to be universal, which means that they have to be reversible as well. So the X Pauli or Pauli X is this, like it's just a matrix that will be applied to your gate. And basically what it does is just a rotation around X axis. Like X of 0 is going to be 1 and X is 1 going to be 0. So this is quite clear. Again, if I have the Blight sphere, and let's say I am in a state 0, and this is my X. If I do a rotation around X, it will bring us from this point to this point. So we go from 0 to 1. So you can say, like, if we applied X to state 0, it takes us to state 1. And the opposite of that, obviously. Now we have Pauli Y also. Pauli Y, the matrix representation is like that, and it's just a rotation of 180 degrees around the y-axis this time. So if you have y0, so you're applying y gate over state 0, you're going to get I1, and y over 1 going to give you minus I0. So you're basically doing both flipping, because you see here, the state 0 is flipped to 1, and also the phase change. The phase change from 1 to here to I. So you see, got a phase here. It didn't have a phase originally. Or here, the phase also changed to minus I. So that's all about the Y gate. Next, we have Pauli Z gate. Pauli Z gate is just, again, rotation over Z axis. If your state is 0, and you apply a Z gate, nothing changed because it's a rotation around Z axis. You already are on top of the Z axis. And if you are applying this to 1, you get minus 1, which you add the phase to your state. And this is the matrix that you use it. And if you are, for example, in a state Z, plus, and you apply a Z gate, it takes you to minus. Hadamard gate, that is extremely important, and it creates actually the superposition. If you apply it to state 0, it will take you to state plus. If you apply it to state 1, it takes you to state minus. And usually this is the first gate that we apply in quantum computers, because it takes us from the initial state to the superposition state. We have S gate, that you can see the matrix. Basically what it does is a 90-degree rotation around the Z axis. And we have T gates, that is a 45-degree rotation around the Z axis. And these are the relationship between T and S and Z, because S is the square root of Z and T is the square root of S. And T is an expensive operation, but it's very important, and we need that actually. I just talked about some specific type of gates, but actually you can create even your own gates. We have that freedom. You can just define how much theta you want to rotate. So based on that, you can define new type of gate, which is also very nice. So at the end of all this gate that are applied to your quantum computer, you have to measure it, right? So when you measure the quantum state, it will collapse, which means that it changed from a wave to a particle. So you cannot return back to the previous state the moment that you measure it. So just know that the moment that you measure the quantum state, you're gonna end up in 0 or 1, no other state. And we have also partial measurement. So if you have if we have two cases here, if they are in the product state, which means that the two qubits are not entangled, measuring qubit 1 will not affect qubit 2. But if they are entangled, measuring qubit 1 will immediately determine the state of qubit 2 as well. And this is what Einstein called it as a spooky action at a distance. Because regardless of how far two qubits are from each other, measuring one will give you immediately the state of the other qubits too. And you can have also the expectation value that you can have bra operator kit sandwich here. It's just for computing the weighted average of all possible measurements. Don't get so worried about this. Later on, we'll get back to that. So how quantum circuits are shown, we have horizontal line. This is basically the way that we show quantum circuits. We have multiple horizontal line, each of them showing 1 qubits. So let's say this is qubit 1, this is qubit 2. And finally, we have a classical bit at the end because you have to measure and store it somewhere. Classical 1. So here we have multiple gates here. For example, here we can have an Hadamard gate, or here we might have an Z gate. And at the end, we have to measure it. So here at the end of each line, we have to measure the state of our qubits. And I'll show you in practice later. Don't worry about that anyway. So we have a set of universal gates. If you have H, S, T, and C NOT gate, I'll show you C NOT in the later session. This 4 gates actually, you can create any other type of gate with them. So that's why we call them universal. For example, H, S, and C NOT are not universal. This is called Clifford group. You also need an T gate to make a universal set. No cloning theorem means that it is not possible to create a copy of the qubit because the moment that you measure a qubit, you destroy it. So you cannot copy qubits. And this is very important also for the sake of cybersecurity, because if you are sending 1 qubit from Alice to Bob, if someone measure it or someone try to duplicate it, simply doing that will destroy the qubit state and collapse it to either 0 or 1. So Bob also will realize that someone tried to intercept the channel. So this is usually the way that you do it. First, you initialize your qubit into 0 or 1. Yeah, sorry, there's a bit of issue here. Into 0, it should be like this, 0. And then you apply an Hadamard gate, and that Hadamard gate will take it to plus. And then you apply a Z gate, and that will take it to minus. And then you apply again an H gate, and that takes you to state 1. You see, this is a transition from state 0 to state 1. How many gates you need? 1, 2, 3. And actually, this is equivalent to applying just 1 X gate. I could just apply 1 X gate and get from 0 to 1, which is also very interesting. So yes, the key takeaway here, just draw. So you have learn how to present information as complex vector. I showed you that the quantum state is shown as alpha 0 plus beta 1. And you know that if you want to find the probability of the state 0, you have to find alpha squared or beta squared will give you the probability of the state 1. And you learn also that alpha squared plus beta squared should be equals to 1. And we learn about the spooky action of a distance that will actually, I'll just simply mention it. Later, I'll talk more about it. Basically, if we have two qubits that are entangled, measuring the state of one of them will immediately tell you what is the state of the other one. And I'm going to show you a little bit of representation here to see better the concept. Hopefully, I can help so you understand it better. I just checked that if you see it as well. Yeah. So this is a website that is called blotch.kherb.io, which is a very nice website. Let me return it to the initial state. So initial state is 0. So I told you that first we have to apply an H gate. You see Hadamard gate. I applied H gate and it took me from 0 to plus. And now I applied another Z gate. You see, it takes me from plus to minus. And then I applied another Hadamard gate, and that takes me from minus to 1. So I did the transition from 0 to 1. I could do all the same just with an X gate. You see, if I apply just an X gate, it directly takes me from 0 to 1. What else to tell you? If you apply an Hadamard gate at the beginning to the state 0, you see, it creates a superposition because now you are actually right in the middle of the sphere. The distance that you have from 0 and 1 is equal. So if you do a measurement here, there is the same chance that you end up in 0 or in 1, which is very nice. And here I'm going to show you a quantum simulator website that is called algasscert.com. So you can apply any gate that you like and you can see even the result, which is very cool. Let me just get rid of this here. Okay. So let's see on the first qubit that I have here, the state is 0. I apply a Hadamard gate. And you see now I have the same chance of getting 0 or 1. Or I could, on the second qubit, I can apply a Z gate. And if I turn this on, this should take me from a state 0 to a state. No, it's not going to actually do that. Because if I am in a state 0 and applying a Z gate, nothing will happen because I'm already on the Z axis. So let me take this out. I have to apply a ZX gate, sorry. If I apply an X gate, you see it takes me from a state 0 to state 1. This is not exactly the X that we wanted, but it just shows you that it takes us from a state 0 to state 1. Let me see if there is something to show this better. Not X transpose. I want to do an X. Okay, maybe this X detector here. No, this is not what I wanted. Oh, now this everything crazy, but that's fine. Yeah, I'll show you in the next session. I have to figure out, or maybe I stop here one moment. Or show you. Wait one moment. I just stop. Yeah, okay, I'm back. So I had to create actually the X gate myself. It's very easy. If you go to the make gate, and you can define a name around which axis you want to turn. X gate is turning 180 around X axis, so I call it X, and 180 that I'm turning around X. I don't need a global phase. When you create, it will create this X gate for you. You see now if I add it, you see a state change to 1. Originally it was 0. By adding this X gate, it will change to 1. which is pretty cool. We'll use it more often. I'll show you different type of things that you can do it, and then we go to the real quantum computer. Yeah, thanks so much for watching and have a great day.